All right, sweet. Um, all right, so we are trying to find the derivative. It doesn't say with respect to what. We're going to assume with respect to y. So the y derivative of g of y. But the problem is that g of y is defined as this ugly thing, like this. Okay, so if you look at the Discord, like literally above my first comment, someone else posted a picture of yeah, someone else posted a picture of the fundamental theorem of calculus, the FTC. That is technically the formula you need to use in order to do this. I have a personal habit of like ignoring that because it's kind of a little weird for me, so I just like to do this from scratch. But basically, the idea here is that this ugly thing, right? You don't need to think about what this is because a derivative and an integral are kind of like inverse operations, right? An integral is an antiderivative and a derivative is a derivative. So they should kind of undo each other, right? So you don't need to focus too hard on this mess in the middle. So what I'm going to do is I'm just going to call it a function. I'm going to call it like f of t, right? So what we're trying to do is we're trying to take um, the derivative of the integral of this random function of dt, right? Where f of t is equal to t to the fourth sine t, right? Or to the 14th, Jesus. Okay. So the way you do that, just from first principles, is when you do an integral, you take an antiderivative, right? So what I'm going to do is I'm going to simplify this like highlighted portion here. So that means the d dy is still out front. But anyways, the highlighted portion, you take an antiderivative, and you're going to get some random antiderivative that we don't know how to find, right? So we call it capital F, which is the antiderivative of lowercase f. And then what we're going to do is we're going to plug in the top limit of integration, right? And then subtract what we get when we plug in the bottom limit of integration, right? Antiderivative, plug in the top, plug in the bottom. Very, very normal integral stuff. And then what we're going to do is we're going to take the derivative of all this junk, right? So the thing to catch here is that the second term here, this f of 8, is a constant, right? Whenever you plug in a number into a function, your output should just be a number, right? Maybe a decimal, maybe a fraction, whatever, but it's still just a constant. So when you take the derivative of a constant, it's going to go away, right? And then what's going to happen on this first term is we're taking the derivative of an antiderivative. So that means you're just going to get back to where you started, right? So the derivative of the antiderivative of f is regular f, and y is sort of on the inside, right? So all we need to write down for our final answer is f of y. Well, f of y means we need to look at the original function, f, right, and just replace the x variable, quote unquote, with a y, because that's what I have written over there. So we're going to have y to the 14th times sine y. That's it. So you don't have to do any product rules, any quotient rules, any of that ugly stuff, right? The answer is just sort of staring at you in the face right from the start. So, like, no, technically you don't have to walk through this thought process every single time because this is just, quote unquote, a formula that you're supposed to memorize. But, hey, it's honestly not that awful to think about the nitty gritty. And this will help you in the specific case when they give you like functions of the variable as your limits of integration. So if they give you like an integral from 8 to y squared or something, this will allow you to deal with that. So if I modify the problem, if I just sort of jam a y squared up in top there this whole time, right? Now we realize that the derivative here, when we take the derivative of capital F of y squared, you would have to take a chain rule because you have y squared inside of a function. So the derivative of capital F of y squared is the outside derivative, f of y squared, and then chain ruled multiplied by 2y. So we'd have to take the original f, plug in y squared, and then multiply our final answer by 2y, and then that would get you the final answer. So it'd be y squared to the 14th, so y to the 28th sine y squared times 2y, and then you can clean that up. So that's how you would do the harder version of this problem, where you have to do a second fundamental theorem of calculus with a function as a limit of integration. Yeah. Alrighty, cool. You playing Terraria?
I forgot how to get to hell, so I keep jumping into lava.
What if it was 1 over y? Just y is the first problem we did, right? Oh, instead of just y. What if it was 1 over y? I mean, we can walk through that. So if we had, again, some number, it doesn't matter what number it is. Like this, is this what you mean? Integral from something to 1 over y, and we're taking a derivative of whatever it was, right? I think that's what it was. Like this? Yeah, okay. Exact same thing, right? So you get some antiderivative with the top plugged in minus some antiderivative with the bottom plugged in, and you take a derivative of that. The derivative of the antiderivative of an inner function is still just a chain rule. So you take a derivative of capital F is lowercase f, and then 1 over y has to stay put, because chain rule says you only take one derivative at a time and you work your way outside in. So you would get the derivative of capital F is lowercase f. And you have to multiply by the derivative of 1 over y. And the derivative of 1 over y is negative y to the negative 2. Because, 1 over y is the same as y to the negative 1. And then the same thing happens on the second term. Second term's a constant, derivative of constant is 0. So we would get this, and then we just have to write this out. So 1 over y plugged in is 1 over y to the 14th sine 1 over y times negative 1 over y squared, right? And you just clean this up, you simplify it. But it should feel very similar to that y squared example that I did. Because it behaves the same way. They can also give you two variables, right? A variable up top and a variable on bottom. And you just repeat this analysis, and it should get you to the correct answer. So that's why I'm not really a fan of the formula for second fundamental theorem, is because it kind of misses a lot of the nuance of this whole upper limit, bottom limit, inner function, outer function business. But yeah.